In the previous lesson, we learned how to write numbers in scientific notation. Today we're going to use those numbers in scientific notation with multiplication and division, and you can even use them for addition and subtraction, although it's easier to add and subtract numbers in standard notation. So today we'll be focusing on multiplication and division. But before we get to multiplication and division, we're going to look at putting numbers in scientific notation in order. So if we start with three numbers and we want to order them from least to greatest, our first step would be to put them all in the same notation. And since we've been working with scientific notation, it will be good practice for us to put them in scientific notation first. So let's start with the 103,400,000. We know that the decimal has to go between the 1 and the 0 because we can only have one non-zero digit to the left of the decimal. Then in order to get from that 1.034 up to 103 million, we have to figure out how many places we move the decimal space, which was 8. So that's 1.034 times 10 to the 8th. With 80,760,000, we know that our decimal goes between the 8 and the 0, so that we have one non-zero digit to the left of the decimal. And we count how many times the decimal place had to move, which is 7 spaces. So we want to order from least to greatest. Now when we have numbers in scientific notation, the least numbers are the ones with the lowest exponent. The reasoning is this number had 10 powers of 8 in it, which put it at 100 million. This only had 7 powers of 8 in it, which put it at 80 million, which is, of course, smaller than 100 million. So the smaller the exponent, the smaller the number. So two of the numbers have an 8 for the power of 10. So the least one is the one that has the 7, 8.076 times 10 to the 7th. Then, when we look at the two with the same exponent, we just look at which one is a smaller number. So the other two numbers both have an exponent of 8 on their power of 10, but the smaller number is the 1.034 times 10 to the 8th. Because that would have been 103 million like we were looking at. The other one would have been 780 million, which is larger. So there's our numbers from least to greatest. Now, let's look at some multiplication, division, and even raising scientific notation numbers to exponents. Let's start with multiplication. So if we have this product right here, the first thing we want to remember is that we're actually multiplying four numbers here. 8.5, 10 squared, 1.7, and 10 to the 6th. Now the commutative property of multiplication tells me that I can put these in a different order. 8.5 times 1.7 times 10 squared times 10 to the 6th. And that doesn't change the value of my number. Now on my calculator, I'm going to do 8.5 times 1.7, and I get 14.45. But I don't need my calculator for 10 to the 2nd times 10 to the 6th. I know that I just add my exponents. The last thing I want to do is check and make sure that I'm in the right notation. 14.45 is not proper scientific notation because it has more than one non-zero digit to the left of the decimal. So I have to make that 1.445. Now since I had to move the decimal one more space, I need to add one more to my exponent, bringing me up to 1.445 times 10 to the 9th. Let's try one with an exponent. 1.5 times 10 to the negative 3rd squared. Now, my power of a product property tells me that when I'm raising a product, which is what a scientific notation number is, to an exponent, I raise each individual factor to that exponent. So I would be doing 1.5 squared and 10 to the negative 3 squared. So I double check on my calculator, make sure that I remember 1.5 squared is 2.25. And then I use my exponent property, 10 to the negative third squared. That's power of a power property, which tells me I multiply my exponents to get 10 to the negative 6. Then I just want to double check and make sure that I'm still in proper scientific notation. Since there's one non-zero digit to the left of the decimal, I'm good. There's my answer. How about division? 1.2 times 10 to the fourth over 1.6 times 10 to the negative third. Now the cool part about this is I can divide these parts individually. 1.2 divided by 1.6 and 10 to the fourth divided by 10 to the negative third. So 1.2 divided by 1.6 is 0.75. And when I'm dividing two numbers with the same base, I subtract the exponents. So 4 minus negative 3 is positive 7. So now I have 0.75 times 10 to the 7th. But is that in proper scientific notation? It's not. The decimal should be between the 7 and the 5. So I'm going to change that to 7.5, and since I had to move the decimal one place back to the right, I need to take one off of my exponent. So I have 7.5 times 10 to the 6th. Let's try it in a word problem. Blood flow is partially controlled by the cross-sectional area of the blood vessels through which the blood is traveling. Three types of blood vessels are venules, capillaries, and arterioles. Capillaries only has one P. I should take one of those out. Now, I'm given the radius of each. The radius of a capillary is 5.0 times 10 to the negative third millimeters. The radius of a venule is 1.0 times 10 to the negative 2 millimeters. And the radius of an arteriole is 5.0 times 10 to the negative 1 millimeters. Now they want me to let R1 be the radius of a venule. They want R2 to be the radius of a capillary, and they want to find the ratio of R1 to R2. So I'm going to take the radius of the venule, 1.0 times 10 to the negative 2, and divide by 5.0 times 10 to the negative 3. What do I get when I divide? Well, I use the same process I used in the last problem. 1 divided by 5 is 0.2. And I subtract the exponents. Negative 2 minus negative 3 gives me positive 1. So that equals 2. It's 2 times 10 to the 1 power, which is 2. So this tells me that the radius of a vein is twice the radius of a capillary. Okay, now we want to compare their areas. Well, area 1 will be the cross-sectional area of a vein, which, since it's circular, we do pi times the radius squared. And we want to divide that by the area of a capillary, which would be pi times the radius of a capillary squared. So let's take that ratio and simplify it. Lost my connection here. There we go. Okay. So the first thing I need to do, but before I deal with all the exponents, let's just notice that our pi's are going to cancel out. the pi on top will reduce with the pi on the bottom, so I can cancel those two out. Then I'm going to square the radius on top, which would be 1 squared, which is 1, and 10 to the negative 2 squared, and I multiply my exponents to get 10 to the negative 4. We can do the same thing on the bottom. 5 squared is 25. And I multiply my exponents, which gives me 10 to the negative 6. Now, before I try to put the bottom in scientific notation, let's just divide. 1 divided by 25 is 0.04. And when I subtract my exponents, negative 4 minus negative 6 gives me positive 2. So if I write that in proper scientific notation, I've got to move the decimal 2 places to the right, and I get 4 times 10 to the 0, which is just 4. So the area of the venule, the cross-sectional area of the venule, is 4 times that of the capillary. So we notice that the ratio of the radiuses was 2, the ratio of the areas was 4, which is 2 squared, which is really, really interesting, and that always happens when we're comparing areas and radiuses. We get the ratio of the radiuses, and we square it, we get the ratio of the areas. I'm going to give you a few to try on your own. I'll have you pause the video and work them through, and then unpause the video and see how you did. So here's the first one, using an exponent. Then we'll do one using a quotient, 4.5 10 to the 5th over 1.5 times 10 to the negative 2. And the last one will be a product, 1.1 times 10 to the 7th, 4.2 times 10 squared. So give those a try, and then unpause the video and see how you did. Okay, on top, we start by squaring each. 1.3 squared is 1.69. And when we apply the exponent to the 10 to the negative 5th, we multiply the exponents and we get 10 to the negative 10th. So we see that's already in proper scientific notation because it has 1 decimal place to the left, or 1 unit, 1 non-zero digit to the left of the decimal place. So that one's all set. 1.69 times 10 to the negative 10th. The next one, we divide these parts here, the 4.5 divided by 1.5, which gives us 3. Then we subtract our exponents, and 5 minus negative 2 is the same as 5 plus 2, which is positive 7. 3 times 10 to the 7th. And that one also 1 non-zero digit to the left of the decimal, so that one is done. Okay, the last one, we can reorder, do 1.1 times 4.2, and 10 to the 7th times 10 squared. 1.1 times 4.2 is 4.62, and 10 to the 7th times 10 squared, we add our exponents and get 10 to the 9th. And that one also is already in scientific notation because it has 1 non-zero digit to the left of the decimal. So we're done. All right, if you have any questions, feel free to ask. If not, you can move on to your homework.